Weed Wacker!
Alright, y'all, let's start where most of the fluid motion begins, the centrifugal fan. As you can tell, the volute's primary function is to guide the flow smoothly from the impeller exit to the pump discharge while minimizing losses. To achieve this, there are two key design principles. The uniform speed principle says that the most efficient volutes tend to be the ones that lead to fluid speed that is uniform around the periphery of the volute. If velocity varies, then we see shear layers and dissipation and energy losses. Second is uniform swirl principle, which is based on treating the volute flow as approximate potential flow, which is isentropic. Real flows obviously have some viscous dissipation, but designing the volute as close to potential flow as possible reduces these losses. To reduce these losses, design goals have the fluid in the volute initially move at the same azimuthal speed as the fluid exiting the impeller. This condition is imposed to the flow rate per depth relationship, which you can see in the third equation. If we take the impeller blade as a control volume and the control surface as the inner and outer edge of the impeller, including the path lines, and we apply conservation of mass, we can get an equation for the radial velocity. These impeller blade airfoils are shaped as logarithmic spirals. The volute is shaped as an Archimedean spiral, which moves outward at constant rate. Thus, clearance between the impeller and volute varies linearly from radius 1 to radius 2.
An interesting design choice lies in turbo machine selection for cooling of the cylinder block. From thermo, we know that the cooling from forced convection is proportional to flow rate. For efficient cooling then, and referencing the specific speed equation, we know that for high flow rate we get a high specific speed. As a result, an axial flow turbo machine may operate more efficiently in this use case. However, the Weed Wacker's physical design constraints lend more to a radial flow turbo machine, hence the centrifugal blower that we see in use. Our Weed Wacker includes a cleverly designed fuel system where gas flows from a gas tank through a diaphragm pump to a pre-carb metering chamber. From there it is pulled into the carburetor, mixed with air, and directed to the cylinder intake. Weed Wackers are designed to operate in a variety of orientations, meaning the fuel tank is often vertically located below the carb. This means there is a non-negligible gravitational potential energy per unit volume term to the Bernoulli equation, which increases the head required to maintain flow in the piping system. When combined with viscous losses in the fuel lines, we can see that the pressure difference generated by the Venturi effect in the carb is, alone, not great enough for reliable fuel flow. This effect is exacerbated when the engine is idling. At slower RPMs, the flow velocity decreases in the carb, subsequently decreasing the pressure difference that pulls the fuel in. This necessitates the presence of a diaphragm pump, which uses the changing pressure in the crankcase as the piston oscillates to consistently pull fuel through the system to the metering chamber. The metering chamber acts as a staging area where the carb can reliably pull fuel from, benefiting from independence of physical orientation and decreased viscous losses due to the smaller distance from the metering chamber to the carb throat. This means that to maintain proper mixture, the carb can generate a smaller pressure difference, decreasing the required flow velocity, which is desirable as we can ignore the effects of compressible flow.
Another fluid aspect of the system is the fuel line, in which we can calculate pressure drop due to viscous losses. The engine specifies a CC of 31.4 and an RPM of 7,000, from which we can calculate the total volumetric fluid flow in through the carburetor. When combined with the standard stoichiometric ratio for an air-fuel ratio of 14.7 to 1, we are able to calculate the gasoline's volumetric flow rate and therefore velocity through the fuel line, yielding 0.018 meters per second. From our measured fuel line diameter, the density and viscosity of our fuel, and its speed through the fuel line, we were able to calculate a Reynolds number of 86.125, which implies laminar flow. When flow is laminar, we find a viscous dissipation factor of 0.743, using the equation FD equals 64 divided by the Reynolds number. We can then find the pressure losses in the fuel line using the Darcy-Weisbach equation. This number was calculated to be 2.42 pascals, which is a low pressure drop when compared to the atmospheric pressure. This signifies a good design. If the pipe caused a larger pressure drop, the carburetor would have to make up for the larger pressure difference when pulling in gasoline.
The carburetor is responsible for mixing the air and fuel mixture right before it enters the cylinder for combustion using the Venturi effect. The choke and throttle are butterfly valves that limit the mass flow of the air and fuel mixture. We measured the diameters at the choke and throat and applied the conservation of mass to find that the velocity of the throat is 4 times the velocity of the intake. Applying the Bernoulli equation to this result, assuming a pressure drop to 97% atmospheric, shows an intake velocity of 18.2 meters per second and a throat velocity of 73 meters per second. This confirms our incompressible assumption, and a quick check with compressibility effects shows little change. From this, we can calculate an airflow rate of 0.0045 meters cubed per second. If we assume negligible fuel mass flow, we can calculate an engine displacement of 38.6 cc, which is higher than the engine spec of 31.4 cc. This is likely due to viscous losses in our steady flow assumption, as air is only drawn in during the intake stroke. A measurement of the cylinder finds an internal displacement of 32 centimeters cubed, which is extremely close to the spec.
Whoa! That video is pretty cutting edge.